Let's continue talking about the modeling for single generators. Um, so we start from this transformed voltage equations, which can be categorized by an equivalent circuit shown here. So after the path transformation, so we'll have the D axis, Q axis, and the zero sequence circuit. So for the zero sequence circuit, which only useful under any unbalanced conditions, for steady state and balanced condition, usually the current will be zero. So we can ignore this circuit for the most of the rest of this course. Later, if we talk about circuit fault current analysis or short circuit study, we can bring this circuit back. So we'll focus on the circuit in two axes. The first is in D axis. For simple rotor generators, it has the field winding and one damper winding. So it will have two circuits on the rotor side and one circuit on the stator side. So in Q axis, only have one damper winding. So we have one rotor circuit and one stator circuit. So the coupling between the D and Q axis are ignored. So on this specific generator, so you can tell in the D axis, it's like a three winding transformer. It have a three windings and which are coupled by electromagnetic field. So we need to model the mutual inductance between any two windings. In Q axis, we only have one rotor winding and one stator winding, so there's basically just two winding transformer. But later, if you want to model the round rotor generator, you may also add one additional damper winding, right? So it will become a three winding transformer also in the Q axis. So this equivalent circuit is pretty much using the transformer as an analogy to study the generators. But one key difference between the generator equivalent circuits from the transformer equivalent circuits. So in this circuit, so this is really the true source, which is the field voltage, which will generate the field current. So that can help build up the magnetic field together with the current induced in the stator winding. So for transformer, this EF will be pretty much the source of the entire circuit. But compared to transformer, we know there's two speed voltages. This one is actually a voltage proportional to flux linkage in the Q axis, and this voltage is proportional to the flux linkage in D axis. So based on the Faraday's law, so the total voltage you can generate for the system side, which has the ED and EQ as two components. So that one depends on the change on the electric field and also a speed voltage, which can be treated as product of the speed and the magnetic field. So in our case, that is the rotor speed multiplied by the flux linkage, which decompose into the D and Q axis component. So for generator, the power from the field voltage is smaller than the voltage, the power generated by the speed voltages. So these two, the speed voltage, is really the most important source for the generator and also for the rest of the power system. Definitely, so if when the generator speed becomes zero, omega r is zero, it's not revolving, and this atom will be gone. So the main power will be from the field voltage. So the generator will downgrade to a transformer. So we need to introduce the per unit representations to simplify the equation, because for the generator we have a stator winding and the rotor winding, and the rotor windings are isolated from each other. So each one will have its own voltage and current level. But when we talk about the model, we want to have the whole set of equations, and we don't want to bother remembering the unit or the voltage or current level for each individual current. So it will be a smart choice to introduce a per unit representation. Per unit representation is basically just give you a percentage number for any quantity. So for circuit, we have four fundamental quantity. We have voltage, current, power, and impedance. And when we study dynamic, we also introduce a frequency. So we have five basic components. Think about how many independent components we have. For the first two, there are two independent components, and also add the frequency. So we have three independent components. So only just need to give those three, maybe two from the first four, and also the frequency. So you'll be able to come up with the base quantities of all the five. So we start from the stator side to introduce how to define the base quantities. So we can use the machine rating. The machine rating is usually based on the stator side, because the stator is really the part of generator connected to the power system. So if you look at the plate values for any synchronous machine, it will describe the voltage level. So usually we pick a line to neutral voltage for the peak value as the base quantity. For the current, we pick a peak value of the rated line current on the stator. Frequency, that's basically the synchronous frequency for the power system to operate. For 60 Hz system, so this base frequency is just 60 Hz. For power base, we use three-phase apparent power as the power base. So to calculate the three-phase apparent power, first we need to change each peak value of voltage or current into the RMS value. So we divide the peak value by square root of 2, and this one will give you the apparent power for one phase. Then you multiply by 3, you will have the three-phase apparent power. Then next one is for the speed. Speed is basically similar concept as frequency, but we change the unit to reading per second. So speed is defined to be the frequency multiplied by 2 pi, right? So if the frequency is 60 Hertz, the speed or electric speed will be 377 reading per second. This is based on the assumption the generator has only 2 poles, such as a gas turbine generator. But if a generator has more poles, so you allow the rotor to revolve at slower speed, while the frequency it generates can still be at 60 Hertz. So for instance, if you only have 2 poles, so this rotor speed will be same as the electric speed, which is 377. But if I have 4 poles, the speed can be just half. Next one is new to most of you. So we also need to define the days for time. You may wonder, why do we want the base value for time? Can we just use the time always in second? Yes, you definitely can, but that will make some of the equation we'll see later be more complex. So when we try to derive the equations to model generator, we want the very simple equations. Sometimes if you know which parameter will have meaning of time, you can assume that the default unit will be second. But when the equation become more complex, it will be more convenient to treat everyone to be in per unit. So then we need to define the base quantity. So here a convention is to define the 1 over speed base as the time base. So which is 0.0027 second as 1 per unit time. So then you will generate, if you have the time constant or any time parameter divided by this unit, by this base, you will generate a number without any unit. So that the number will tell you the time in per unit. Impedance base will be calculated directly from the voltage base divided by current base, and you can also use the power base and the current base to come up with this impedance base. So inductance base is based on the definition in physics. So the inductance is equal to impedance divided by the angular frequency. So you can get this inductance base. The flux linkage base, by definition, is the inductance multiplied by current or voltage divided by speed. The next one is the torque base. Torque base is defined as the power divided by the speed, right? So if you know the power base and the speed base, you will be able to calculate torque. So this speed is actually the mechanical speed, not the electric speed. So which is the slower speed, right? So when you have more than 2 poles. So this one will tell you the true torque. And using this base, you can change all the torque into per unit. Okay, so next one, we want to talk about the radiance, because later we'll see a lot of radiance. Radiance means basically here for it's just the same meaning as inductance. For radiance in per unit, that's actually radiance divided by impedance base. And that is equal to this formula. That is equivalent to the true inductance divided by the inductance base, and here we have frequency divided by frequency base. Okay, so those 2 pi can be cancelled, and actually this formula become the frequency in per unit multiplied by inductance per unit. So that will give you the radiance in per unit. So this is pretty obvious because usually radiance is defined to be, you must remember this formula, right? Angular frequency multiplied by L. So in per unit, there will be something on frequency multiplied by something by the inductance. Okay, so here then we can have a conclusion. So if you have a power system, its frequency can be exactly at frequency base, for instance 60 Hertz, then the inductance and the radiance in per unit will have exactly the same value. Okay, so that's very convenient. So if your frequency can maintain at around 60 Hertz, so later in the equations, you can always replace any L by X or X by L. So that is why some software on power system simulations, they like to use L everywhere, but actually which can mean radiance, or some other software use OX. So in the later equations, we will use X for the equations about voltage, where you will see the X multiplied by current will give you some voltage drop on certain branch of the inductance. If it's in the flux equation, we'll use XL. That is more meaningful. But you may ask, what if the frequency is different from the frequency base? Actually, in modern power system, frequency variation need to be limited within half hertz. So if you operate a 60 hertz system or even 50 hertz system, so you divide the half hertz by 60, that one is less than 1%. So which means that is pretty much how the frequency may vary in real system. Beyond this 1%, usually the frequency protection will react. So this means if you treat all the L as S, so all S at L, the largest error you can introduce is just 1%. So that may not be significant to rise up your calculation. So that's why many software just simply assume those two to be equal if you don't care about this 1% error. So next we need to talk about the rotor. So first we create this table for the stator winding D, Q, or zero axis. We already defined the base frequency, the base voltage, and base current. For the three rotor winding, because they are not connected with each other. So the only way connecting the rotors and the stators actually the magnetic field and the frequency. So for rotor, we use the same frequency base, and also we use the power base. And we still need to define the current base for each winding in rotor. Then we can finish all the five base quantities for rotor side. Okay, so this is the traditional way to define the base, and we have the freedom to select what current base to use. So one idea is we can select the current bases for the three rotor winding, such as we can generate a symmetric per unit inductance matrix. Okay. So this is the inductance matrix, right? And we want to first this is transform the inductance matrix up to the power transformation. So you will see those coefficient K there. And what is K? If you remember, so let's go back to the power transformation slide. The K here is K0, KD, or KQ, right? So K is related to those values. And later when we derive the inductance in the transformed circuit, and K here is square root of 3 halves. Okay. So if you don't use the orthogonal power transformation, so that is possible. The K can be different value, and those two components may not be equal. So you may not generate symmetric inductance matrix. So you can choose the base quantity for the currents for the rotor winding, such as the inductance matrix, to be symmetric. And finally, we hope for any mutual inductance, like for instance, we can introduce the mutual inductance coupling the stator windings, and also coupling the stator winding with rotor winding, all the same value. So this one can largely simplify the inductance matrix in per unit. Okay, so let's take a look at the detailed step or some formulas we need to satisfy to make this happen. So the idea of this result in per unit is to generate inductance matrix for the mutual inductance coupling the stator winding. So one stator winding and rotor winding are all same. So this item is actually the sub inductance, and this one is the leakage inductance, and this item is the mutual inductance coupling the stator winding. And we hope this one to be equal to the other mutual inductances involving the stator windings in D axis, and in Q axis we have a similar same mutual inductance also in Q axis. So that largely simplify the inductance matrix. Okay. So as I said, so LAD is actually the mutual inductance in the D axis. So to calculate the per unit, it will be LAD divided by the stator inductance base. Okay, so if we make this part of equation hold, that will be able to change this item and that item into LAD, both into LAD. Okay, which is same as the mutual inductance in the stator one in DSs. And if we also make this equation hold, that will change this item in per unit also into LAD in DSs. So proof of this formula, like first starting from this equation, we can actually, the idea is very simple. You can just you pick two equations, right? Because you want to, let's say first how do we make the KF the KMF and be equal to LAD. So we just pick two equations that involve KMF, which is first is this equation. So this row multiplied by this column, you generate first equation. So that equation is not in per unit, but you divide both sides by the base quantity you already defined from previous slides. And second, you introduce another equation, which is this row that also involve this MF, multiply this row, multiply also by this column. So let's talk about how the flux linkage in the field winding are coupled with the current in the DSs. So both equations you divide the base quantity, and finally you need to make the per unit value of those two to be equal, right? Which correspond to those two to be the same. So that can easily prove that is possible when this equation hold. Okay, so finally we can use this equation to define the field current base. So starting from Q field current base, you can define the field voltage base, field impedance base, inductance base, flux linkage, and finally you can give it as well for the this MF base. Similarly, we can from this part we can have this formula to calculate the damper current base, and we can also come up with other bases. So in QSs, we can do similar things. We can, if we make this equation hold, that will make this element, that element, those three be equal. And from this equation, we can know how to calculate the IQ. Okay. Okay, so now we have a much similar inductance matrix or flux linkage equation in per unit value. So let's summarize what we have done so far. We start from this very beginning voltage equations, so which has inductance matrix including 36 elements. If we consider symmetric structure of this matrix, so we only need to know the value for the top triangular area. So that has 21 element. Among the 21 element, only 6 of them actually constant. Most of the remaining element are theta dependent. So this is accurate model, but definitely not good model. Remembering we mentioned at the beginning, so the purpose of the generator modeling is to find the smallest set of constant parameters, which can represent the generators without sacrificing any accuracy. So this is accurate model, but there are a lot of parameters which are not constant. Then we introduce the power transformation. we make it a fully constant inductance matrix by generating the circuit not in original ABC frame, but in the new zero DQ frame. This is good model. It has 10 constant inductances because it's still symmetric if we use this orthogonal transformation. So you only need to give the value for the perimeter in the top triangle. So there's only just 10 different parameters. Next, we introduce a per unit system, and we define the base quantities, and also we make sure the mutual inductance in the D axis and Q axis are all same. So which means in the D axis anywhere you see the inductance involving two windings or representing the mutual inductances in the D axis are all same. And for in the Q axis, they're also all same. Okay, so there's only one mutual inductance is not equal to LAD, which is this MR. MR represents the coupling between the field winding and damper winding, right? So that's a coupling between the field winding and the damper winding. So that's involved the two winding both from rotor. But if we think about a generator is well designed and the magnetic field, if it coupled any two windings from stator or from rotor, the total flux linkage will be about the same. So there's a very little leakage flux. So which means even the MR is different from the other mutual inductance in DSs, but which could be very close. So we can even make this assumption. So then we'll have 7 constant inductances. So that's a large reduction compared to the previous step. So then the next step is to find the equivalent circuit based on this simplest voltage equations. Okay, how do we develop the equivalent circuit based on this voltage equation? So we put voltage equation here, and together with the flux linkage equation. So for flux linkage equation, we multiply by P. P here is the operator of differential. So we basically just the first order derivative. Just to make our expression simpler. Because we can notice this part is identical to this part. So immediately we can have this set of voltage equation. So this set of voltage equation, we don't involve any inductance. We use the voltage drop on any resistance together with the voltage drop due to a flux linkage. But that's basically the same equivalent voltage equation. So next step, we want to find equivalent circuit which can be characterized by those equations. So this is the equation in the D-axis, equation for the field winding, and equation for the damper winding D-axis, equation in the stator winding Q-axis, and equation in the damper winding Q-axis. So we ignore the first equation, which is about the zero sequence circuit, which can be neglected if the system condition is balanced. So we will find equivalent circuit which can be characterized by those 5 equations. So basically, we want to find one circuit in the D-axis and one circuit in the Q-axis. So the idea here to generate those equivalent circuit will be using the same branch appearing in different equations for the circuit. For instance, here we have LAD. In the equivalent circuit, we'll assume the LAD as the same branch which has the total inductance of LAD. And if it appear in many items, that means the same branch in the circuit. We're not using multiple branches with the same inductance of LAD, right? That's our idea because we want to find this a simpler circuit. And for this equivalent circuit, we are going to derive, which will be very different from the analogy of transformer. So in this slides, this is also a good equivalent circuit, accurate equivalent circuit, but it's not very convenient to use because stator side, for the coupling in the DICs and or QICs, we have either 3-winding transformer or 2-winding transformer. But right now we want to change the transformer model into the same circuit in each axis. Okay, so how do we do that? So one idea is let's start from the first equation, ED. Let's see what we can generate. So I first basically I rearrange all the items in the equation. I color any item which is related to LAD. That describes some voltage drop on this inductance. Right. So that's this item, and this item. They all merge to the first item. So this first item tells part of the voltage drop of ED is equal to this inductance multiplied by the change of the three current, right? One is the stator current in DSs and the field current and the damper winding current. Okay. And then for the remaining item in the equation, I just color them in orange. Okay, so let's try to draw something based on this equation. So we have on the left-hand side, we have total voltage ED. And then we have a voltage drop, which is categorized by the orange item, which represent those three, right? It's voltage drop on the resistance and the voltage which is equal to the induced voltage due to the Q-axis flood linkage, and then the voltage on the leakage inductance. Okay, so the right item is basically describing what happened on this branch. So that's the same inductance branch carrying three different current. One current going to the stator winding and two currents from the rotor, IF and ID. Okay, so that's pretty good. We already generated part of the circuit, but we haven't explained where those two currents come from. So we need to continue. So then we need to utilize the second equation, the EF. For the EF, since we already generated this branch, we're going to reuse this branch. So we put that branch here, and we also need to explain where this ID plus F from. So we need to generate that current and also find any element which can contribute this current. For example, this element, and also, so this item is basically just a balance, subtract added item for the first item. And then the remaining item will be colored in green. And you see the remaining item is only about the field current. And the pink item is about the total current going through a branch, so that the inductance is equal to MR minus MAD. Okay, so if we continue drawing this branch, which will be something like this one. So the green item is described the voltage drop on this inductance, and it's also the voltage drop on the resistance. And this voltage is actually just our field voltage, right? Okay, so by using the first and second equation, we'll be able to draw this circuit. So it's almost finished, but we still need to explain where this ID come from. Then we need to utilize the third equation. So for third equation, we'll put whatever already existing branch, right? So we'll keep the red branch, the pink branch, and everything else, we just color them in blue. And you see all item is actually describing some type of voltage due to the ID. Okay, so then we finish this circuit. So we'll do a similar approach for the QSs, and we'll be able to generate the second circuit. Okay, so compared to original circuit, which has 3 windings transformer in the DSs and 2 winding transformer in the QSs, and right now we have 2 equivalent circuits, respectively from the D and Q axis, and which is more convenient to use. Okay, all right. So we have the 2 circuit to start with, and they are accurate model. So you either use those voltage equations or use those circuit to build up your power system model to do the simulation. So far, we didn't sacrifice anything, right? We didn't ignore anything. So those models are accurate. Okay, so our future step will be further reducing those equivalent circuits. So if we can add additional assumptions, such as what if the system is under the static condition, and some of the branches will be ignored. So we'll have a simpler circuit. So our goal in the future will be how to merge those 2 circuits into the equivalent circuit we already know, right? So when we use the generator as the equivalent voltage source, so we have some type of EMF and some type of readiness, maybe also resistance as well. We'll figure out how to generate this equivalent circuit, but that will need some assumption and some approximation.